This works, which is important. So I prepared, so today is going to be MHD, fluids, and there's a lot of material here. So it's going to be the opposite of yesterday's two-slide summary of plasma physics, I'm afraid. But I hope that even though you all know most of this, there's some things that you may have not appreciated, put it that way. Okay, so I'm going to start with a very brief review of how you go from kinetic theory to fluids to plasmas and some important parameters that are involved. Then we'll be discussing MHD, just general considerations. Then I'm going to talk about fluid instability and answer the question of why the solar wind is supersonic. And you're going to tell me, but wait, you showed us yesterday why the solar wind is supersonic. Actually, I didn't. I showed you there had to be a solar wind, but I didn't really discuss why it's supersonic. Turns out that the answer is a little bit different from what you've learned on textbooks. Then I'm going to discuss MHD waves and the special big spherically polarized humongous wave that we kind of mentioned yesterday. And then finally, we'll talk about MHD invariance and a slightly different view of the triggering of magnetic reconnection, okay? With, I hope, some insights as to how it can be generalized. We'll see. Whoa, it's a good start. Yeah. Okay, so let's get going. So where do fluid theories come from? Well, this is already, you know what F is, right? It's the one point distribution function. Okay, so that's already a reduction compared to the real kinetic theory, which tells you how many particles are here, how many particles are there, and how many particles are in another place, and has the correlation between them. So this is just saying how many particles are in one little position in phase space. And essentially, there's a conservation theorem. If you don't create and you don't destroy particles, you have the top equation, which is just the conservation of the number of particles in phase space. Now, normally, the acceleration doesn't depend on velocity, and therefore you can pull that out. And when we discuss magnetic fields, we're going to have a special form of dependence of the force on velocity, the Lorentz force. The Lorentz force is V cross B. Well, guess what? Divergence in velocity space of V cross is 0. So we can pull out the Lorentz force as well, even though it does depend on velocity. And so we get the second equation there, sometimes called the Vlasov equations, but we're not there yet because we haven't specified what that acceleration is. Now, the problem is that the force, F over m, which gives the acceleration, can be divided into two pieces. And we're going to do this really in your face. We're going to say, yeah, well, there's like the smoother forces from the average particles everywhere. And then there's the intermittent forces coming from collisions. They could be 2-particle collisions, 3-particle collisions. We're not going to be precise. And that leads to separating F into F, sorry, that's Italian, lentamente variabile, slowly varying, and F collisional. And then depending on the collision term that you use, this becomes Boltzmann's equation. If you use dF by dt collisional with the Boltzmann collision integral. And you already know the mischief that poor Boltzmann and the suffering that poor Boltzmann had to go through when he wrote his collision term, right? If you've ever been to see Boltzmann's tomb, the H theorem is on his tomb. F d by dt of f log f greater than or equal to 0. Okay. All right. Then what do we do when we try to build a fluid? If you're in a neutral gas, there's a kind of a technique. There are books about this technique. You take moments. The problem with moments is your closure. You know, every time you take a moment is essentially some power of the velocity times the distribution function. You integrate in velocity space and you get an equation in physical space. But because there's the convective term, div, the grad of v times f, every time you add a v, you get another power of v, and therefore your continuity equation has the first power of velocity, your momentum equation has the second power of velocity, your energy equation has the third power of velocity, and so on to infinity. Of course, you've taken a 6-dimensional thing, you've turned it into a 3-dimensional thing, you got to go infinite if you want to keep the information. So what do? We close this system. What is Q? You should all know what Q is. Q is what's called heat conduction. Okay, it's the third order moment. W is the random part of the velocity, i.e. you separate V, the velocity, into an average value U and a random part W. And you can go on and you can write your equations. And at some point, you're going to have to decide what you're going to do with Q. Now, what do people typically do? There's a very famous article by Braginski in which he says, what you do, you say that the order zero distribution function is something like a Maxwellian. Then you say F is F0 plus epsilon F1. And you essentially go through a linearization and you close by considering perturbation theory. Okay, that's how you pull out the heat conduction depending on temperature. You're taking your third order moment and you're saying that it's a function of your second order moment, which is temperature. Okay, this is the procedure. I'm not going to go through it because that would be multiple lectures on their own. Okay, this is how you pull out the fluid equations. Now, there's various subtle pieces in this. You'll notice that this is the equation for the total energy. And you'll notice that when you write that out, the total energy here, I've neglected magnetic field. So I'm really talking about a neutral system right now at the moment. And you have the mechanical energy and the internal energy. And then you have the flux of that energy plus the work that's done by the pressure tensor on the flow. And that's why when you take an isotropic pressure, P delta IK, this turns into 5/2 P. That's the enthalpy flux in your convected part of the energy. Okay, and then you have QK. Now the pi IK gives you the work done by viscosity, the non-diagonal parts of the pressure tensor. And that works out so that when you actually subtract, because you can write another equation by taking U dot, the momentum equation, to get the mechanical energy. You subtract the mechanical energy from the total energy and you get the equation for the internal energy. And that's written down here. It's telling you that the change of rate of something that's actually proportional to the entropy has to do with viscous and heat conduction, viscosity and heat conduction. Okay, this is the neutral fluid. Now, then you have ionization, and we're turning the gas into a plasma. When does it turn into a plasma? Well, there's two things. To see when a ionized gas is plasma, you have to consider the Saha equation, which is how many particles end up being ionized with collisions in there. And then you discover something really interesting, that the ionization of a hydrogen gas is essentially complete at temperatures of order 10,000 Kelvin, which is much less than the ionization potential, which is 1.5 times 10 to the 5, okay? And it's also important to remember that a plasma reaches 90% of its conductivity with ionization degree of only 8%, okay? That's why we can think of the photosphere as a plasma, even though the ionization rate is very small. Once we do that, there's some other conditions for this gas to become a plasma. There's a thing called the Debye length, which is essentially the ratio of the thermal speed to the electron plasma frequency. And that tells you the characteristic length over which electrons can neutralize the positive ions. You got to have a lot of particles there. If there are not a lot of particles, then you can't neutralize it. And then you're dealing more with an ensemble of charged particles rather than something that is quasi-neutral on a large scale. And when we talk about plasmas, we normally consider something which is quasi-neutral on a large scale. And a reminder that the plasma frequency is 4 pi n e squared over me. You'll notice that I'm using CGS, sorry, but it's just the way I am. Collisions, we discussed them a little bit yesterday. So how does it turn out that the collision cross-section goes like velocity to the -4? Well, you can do a rough estimate by saying that how close will two charged particles come to each other with a given temperature? Well, you just have to say 1/2 mv squared, 3/2 kT, is equal to the charge potential energy. And then you take pi b squared and you call that the cross-section. That's the rough order of magnitude. And that goes like 1 over t squared e to the 4th. And then the collision frequency is n sigma v. And you end up with this expression here. You can clearly see that electron is going to have an me to the 1/2. Ion is going to have an mi to the 1/2. And what about ion electrons? If you want to create a equilibrium between ion electrons, it's a little bit tougher because It's like having a little Fiat 500 going against a truck on the highway. So in the collision between a 500 and a truck, the truck doesn't notice. 500 does. But the truck doesn't really notice. Only a fraction, ME over MI, of the energy is lost by the truck during that collision. And that means that it takes MI over ME collisions for the ions to equilibrate the electrons. All right, for the same reason, conductivity goes like T to the 5 halves. We discussed it yesterday. So basically, in a plasma, depending on your time scales, you can either consider them to be one big fluid or two fluids, because the electron-electron equilibration time is faster than the ion-ion equilibration time, which is faster than the electron-ion equilibration time. And these all go like the ratio of MI over ME. So the fastest is TEE, then you have square root of MI over ME to get II, and then you have another square root, so MI over ME to get EI into equilibrium. When you're considering a one fluid plasma, you're considering time scales that are longer than that. That's all blah, blah in there. And you do your one fluid closure, and you get the MHD equations, which is going to be basically our playground for the rest of today. Let me just summarize: a continuity equation, a momentum equation in which we have the J cross B force, non-relativistic. So essentially J is C over 4 pi curl of B. We've neglected the displacement current. You have an Ohm's law. And I put a resistivity in here just to show that we can have a non-ideal Ohm's law, but we'll get to that in a minute. But basically, if you can neglect collisions and resistivity, then it's really telling you that the electric field in the frame of the fluid is 0. E plus U over C cross B is equal to 0. You can then write an equation for the magnetic field induction by using d by dt is C curl of E. And when you do that and you replace that, you get curl of U cross B plus blah, blah. Then you have an energy equation. If the pressure is just diagonal, you don't have heat conduction, then that turns just into resistive dissipation appearing on the right-hand side here. And the beautiful thing about MHD is that it has a consistency check, which is not obvious, because charge density comes from the divergence of the electric field. So for MHD to be consistent, the time derivative of that quantity has to be much smaller than, has to be very small compared to the other terms. In other words, put it this way, 1 over q dq by dt has to be much smaller than any other time scale in your system. You can write these equations in conservative form. You can write the magnetic force in terms of a magnetic pressure and a magnetic tension, as it's written down here. You can write these in conservative forms. That's what your MHD codes typically end up solving for. And there's a fundamental theorem that I want to remind you of, which is the virial theorem. What is the virial theorem? How do you write the virial? Let me go back a second. So the virial theorem in mechanics, essentially, normally, how do you derive energy conservation in mechanics? Well, you take x double dot, the acceleration, you multiply it times the velocity, you bring that in the time derivative, you get time derivative of 1/2 mv squared, and then the force is a gradient, you get conservation of energy. Virial comes from a different trick. You do the same thing, but instead of multiplying times velocity, you multiply times position, and you integrate by parts. And then what happens? That if the motion is constrained, a lot of that integral vanishes, and you can write something for the average velocity of your system, as long as it's not free, as long as it's constrained. And you can derive Kepler's laws, all these things, you come from that. The similar thing that's done here is you do exactly the same thing. You take the force, which is written in terms in tensorial form as GIK, you multiply it times the coordinate, and then you integrate over the volume, all right? And you integrate by parts, and what do you get? You get xi GIK dsk on the surface minus delta ik dxi by dxk integral of GIK and dv, okay? So what does that mean? What does that translate into? It translates into the surface term, wherever your boundary is, far away, and this integral in volume. Now let's look at dxi dak. That's delta ik. So you really have delta ik gik. So you're taking the trace of this animal here, all right? So when we take a trace of this animal, what do I get? I get b squared over 8 pi and then I get minus b squared over 4 pi, and I get p, I get 3p, 3b squared over 8 pi, minus b squared over 4 pi. And so I'm left with something which is positive, 3p plus b squared over 8 pi. So I have an integral of a positive quantity. Okay, then I have the surface term, and on the right-hand side, I have 0. If we do this properly and we include the internal energy, the gravitational potential energy, let's call that phi, and the surface term, we get 2t plus 3 gamma minus 1u plus m, where that's the magnetic energy integral of b squared over 8 pi, plus phi plus s equals 0. Kinetic energy is positive. 3 gamma minus 1u is positive. M is positive. Gravity is negative, and surface is negative. So how can you confine a plasma by itself? You can't. You want to make a fusion machine, you need a surface term. You can't confine a plasma with a magnetic field without surface terms, unless you have gravity. That's how the sun does it. Gravity is attractive, right? So remember this, you cannot. The surface term is given by this, and this is what a tokamak provides as far as confinement is concerned, right? So on the sun, when we're talking about the corona, that's not gravitationally settled. So we have surface terms, and that's the photosphere, the anchoring of magnetic field lines in the photosphere, line tying, as it's called. That's what stabilizes things like coronal loops. All right, that was MHD. So now let's get back to our Parker thing. And so it's a fluid. It's a stratified fluid in spherical geometry. And I told you that if T of R falls less fast than r to the minus 1, but with thermal conduction, it falls like r to the minus 2/7, and therefore you can't have a static atmosphere. And then this is Parker's drawing. As you can see, 2 million degree corona, goes up to a few hundred kilometers per second. 1 million degree corona gets to 300-400 kilometers per second. And that's it. Now, because of the fact that you have to have this subsonic to supersonic transition, people discussed this problem to no end. And some very smart people were involved. And turns out that Leon Mestel, astrophysicist who died a few years ago in the UK, he was fundamental in understanding how stars form and how you can get rid of the magnetic field to form stars. To form stars, you need to get rid of the magnetic field from the interstellar medium. Otherwise, stars would never collapse, okay? Anyway, he was quoted in a paper by another fluid dynamicist, Paul Roberts, a very, very well-known fellow, saying that were the temperature at the base of the solar corona 10 to the 5 rather than the generally accepted 10 to the 6, the total pressure far from the sun would suffice to suppress the solar wind entirely. So it's really not true. The justification of the Parker solar wind in terms of the pressure of the interstellar medium doesn't sound too good anymore. Is it just, so what's going on? Well, let's go back and revisit Parker's equations. So the equation that we were solving, that Parker was solving, was especially the static equation, u by du by dr. There was no velocity originally. He was just equilibrating the pressure gradient with gravity, right? And that's how he proved that you had to have flow. But let's include the flow. And let's make the simple assumption that we're isothermal, so the temperature is uniform. You can do that out to 20, 30 solar radius, not a big deal. But then this equation, using the equation of continuity, can be written in two different ways. You can keep this is easy to integrate. You can see that it's a trivial equation, really, because this is the derivative of 1/2 u squared. This is the derivative, if rho and p are the same thing, this is log p, right? Because it's 1 over p dp by dr. And this is gravity. That gives you a 1 over r. So you can integrate that. Let's do it here. And I'm going to normalize the flow velocity with the sound speed. And I've just done that integral right here. And I'm integrating from the coronal base, 0, out to infinity. Okay? So what do I get? I get 1/2 m squared minus m0 squared plus log p over p0 is gr over c squared, where c is the isothermal sound speed, times -1 plus 1 over r. Or, alternatively, I can use that continuity equation to get rid of log p over p0 and integrate the other equation and use just m. So I get rid of p in terms of m, and then the equation is the one on the top. It's trivial as well, all right? But we know the phase diagram of this equation. And the phase diagram of this equation looks like this. It has solutions. It has solutions. It has a critical point, which is where essentially, let's go back 1 second, sorry. If I look at this equation, which is written only for m, you'll notice this is an ordinary differential equation that has a regular singular point on the left-hand side. When Mach is equal to 1, this becomes 0. When 2 over r minus g over r squared vanishes, because close to the sun, r squared wins. This thing's negative. Far from the sun, 1 over r wins, so this thing becomes positive. There's a place where this goes to 0. Okay? So there's clearly a singular point where m is equal to 1, where the flow becomes subsonic. And for this equation, it's trivial. The point where you can actually go through, solve this, it has to have the right-hand side vanish where the left-hand side vanishes. Okay? So if you look at the phase diagram, that's what you're going to get. You're going to get two critical solutions. One comes down through that critical point where both sides vanish at the same time, and one goes up through that. And we're going to call those the transonic solutions. And then you have the famed breezes, so solutions that accelerate, but what happens is that before Mach equals to 1, before that left-hand sign changes sign, the right-hand side has changed sign, so the derivative of the flow velocity goes to 0. The right-hand side becomes negative, so this thing starts slowing down. Okay, it starts slowing down. Or you have supersonic solutions from everywhere, but we know that the solar corona is not taking off. We see the corona, otherwise we wouldn't see the corona if it was supersonic at the sun. And so we have these possibilities. So Chapman and these guys were considering subsonic flow as a possibility. And so people were wondering, how is it? How does the sun know that the flow has to go through this transonic? So that was the question that people had. No, how can you know? It's one solution. You start off, I think, and the thing is so bad that to this day there are papers appearing trying to explain why that happens. Okay, and the papers are almost unequivocally wrong. But let me consider these subsonic flows for a minute. We can integrate for subsonic flows because for subsonic flows, the flow axial velocity tends to 0 as r tends to infinity. So if we go back a sec and look at this equation here, because the flow at large distances goes to 0, we can actually integrate p over p naught. Okay? And what we'll find is that p over p naught goes like e to this times e to m0 squared, and then this vanishes at large distances. So what happens? What happens is that as a function of distance from the star, the pressure goes like this. P0 e to the m0 squared minus m squared over 2 minus gr over c squared. Now, if you have the isothermal static atmosphere, then m and m0 are both 0, and you just find that p static is p0 e to the minus gr over c squared. You have a static atmosphere. Then you can take breezes with different velocities. They all go to 0. But the fastest breeze you can make is something that goes up the transonic, hits the singular point, and goes down again. Instead of continuing forward, as in the Parker solution, it makes a cusp and comes back down. That's the fastest breeze you can make, right? For that guy, what's going to happen? Its Mach number is going to tend to 0 at infinity, but its base Mach number is going to be the same as for the Parker solution. So let's call that P0 e to the m squared over 2 minus gr over c squared. Critical breeze, upward plus downward transonic. Okay. Now, some of you, looking at those two expressions, are going to say, wait a minute, something's weird. Or not. It's a question for you. Just what I wrote down there. P stat is P0 e to the minus gr over c squared. And then I put P crit is P0 e to the m star squared over 2 minus g. Mind you, this is the pressure at infinity. Okay? Okay? So is there something weird about that or not? Well, when I was trying to explain this thing to somebody on a train, when I saw that, well, I didn't get that far. I got that far when I got home. I was trying to tell the Parker solution to a physicist on a train. And as I was telling the story, I was saying, this doesn't make sense. And then I said, I better go back and look what's going on. And when I did this little calculation at home, I said, oops. You see, suppose you have a room like this one with a window, okay? And in equilibrium, static, the difference in the pressure between the room and outside is P stat, okay? Now I create my outflow. That's like opening the window. But I discover that my outflow solution with the window open has a pressure outside, which is higher than the static one. You see that? There's a e to the plus m squared over 2 there. And so I go back and I say, wait a minute, if I'm static and I open the window and the pressure is higher, what happens? If I'm static, I have a window closed, and then I open the window and the pressure outside is higher than the pressure inside. I expect stuff to come in, not to go out. But wait a minute. That equation, m minus 1 over m prime, if you change the sign of m, it stays the same. It's even in m. So that equation is also true for spherically symmetric inflow. What have I just discovered? Just discovered that these solutions don't mean anything for outflow. It's as though they don't exist. That's an assumption. I haven't proven it yet. My assumption is I thought those solutions were there for outflow, but I clearly made a mistake. I mean, mathematically they're there, but if what I'm saying physically is true, they got to be unstable, right? Okay, now let's go back. Let's assume that Parker was right. You go through the sonic point, and then there's this little tiny pressure at infinity, much smaller than those pressures that I'm talking about. Then far, far away, there's got to be a shock, okay? And I put it there. And in fact, how do you put a shock in this? You have to use conservation laws. What is a shock? A shock is a place where you're going supersonic, you don't know what's happening, but you have to conserve energy flux through there, and you have to conserve mass flux. So you apply those conditions, and you find that for an isothermal shock, which in astrophysics do exist because you can have strong radiation at shock, so that basically the temperature doesn't change. Anyway, it's slightly, but it turns into m minus m plus equals 1, okay? That's the condition. So actually, so if you take essentially the upward transonic and then take 1 over m and you connect it to the leg of the double-sided solution, you've done a physically correct solution of the isothermal equations by using this condition, m plus m minus equals to 1, which is the dashed line. The dashed line is just 1 over this line. And so you can connect it here, here, here. And as you can see, it comes up all the way to here. All right. Okay. So now, suppose that you're going through a cloud and the pressure at infinity goes up. What does the shock do? Comes in. Some of you might not believe me. So, no, how do I click this thing so that it will start? See, it does go in, just in case you don't believe me. That's my high-tech simulation. Okay, so let's do the stability. The stability is interesting for reasons that we could get into later on, but it's really simple. You linearize the equations and you look for solutions. And then you can use some of the standard tools of mathematics to kind of prove analytically, back of the envelope, that indeed breezes are unstable. And that's the growth rate of breezes as a function of their base Mach number. The static atmosphere is marginally stable, and that critical breeze, the one that comes up, touches the sonic point and comes back down, is also marginally stable. But all the other ones are unstable. Voila. So the breezes don't exist. All right. The pressure at infinity increases with increasing base Mach number. Now what happens? Take this further. If you have a static atmosphere and increased pressure at infinity, you expect flow to go in, not out. Turns out that those equations had been solved by a very famous astrophysicist, Hermann Bondi, in 1952. This would bring me into a philosophical, historical discussion of Parker and Bondi that I don't want to get into, but there's something there that doesn't quite work. And I know that's for sure. He wrote this beautiful paper on spherically symmetric accretion. If you have never studied this paper, I encourage you all to go and read it. This is like the essence of astrophysics. I'm going to write equations that I don't know how to solve, and I'm going to find all the solutions without solving them. That's what he does. It's a beautiful paper. That's the only place Parker doesn't draw the phase diagram in his article, but Bondi in 1952 does. Not only that, an Irishman, well-known astrophysicist who was visiting California, McCrae, puts shocks in that flow, in the inflow, and solves a paradox that Bondi had found for his solution. 1956, that's before Parker. So let's consider what happens now. Suppose we have our supersonic wind with a shock, and we're going through a cloud. The shock gets pushed in. You increase the pressure, it gets pushed further in. You increase the pressure, it gets pushed further in. How far can it go? Well, it can go here, where you get this critically supersonic flow. It just goes, touches the sonic point, and comes back down again. What happens if I push more? Well, I can't go here, can I? Those were unstable solutions. So what's going to happen? What's going to happen is that all of a sudden, the corona finds out that the interstellar medium has high pressure. It didn't know before because there was a shock. Nothing here knows about what's happening beyond that shock because the flow is supersonic. There's no information coming back. But once it discovers that it's too late. That pressure is overwhelming. The flow collapses into accretion with a shock. Voila. So this is what happens. Comes in, supersonic accretion with a shock. Now, if the corona heats up again so that its pressure increases, on the way back out, can go through the breezes. Because if you think about it without solving equations, the equations for the average flow are even in the sign of u, which means that the linearized equations are odd in the sign of u. But now, in the linearized equations, you have e to the gamma t. Okay? So your solution, the equations are identical, but all the terms change sign except gamma. If I know the solution of the one with positive u, I can get the solution for negative u if I change the sign of gamma, which means that if gamma is positive for outflow, gamma is negative for inflow, i.e. the breezes are stable. No mathematics, but. So that's what happens. So basically, you have a hysteresis cycle. And there's a range of parameters where you can either have an accretion inflow or a supersonic wind with a shock, depending on the history of what happened to the star. You might say, okay, so I wrote this paper in 1994 trying to figure, because I hadn't seen, I talked to people about it, they didn't know about it, so I said, let's try to publish them. The paper was accepted, it was ignored. I sent it to a few people, including Gene, Parker. That's how we got into discussions. But because this is completely theoretical right now, I said, well, now people know how to do simulations, right? So we can do it. I had a PhD student do the simulation. And you start from an isothermal atmosphere, you decrease the pressure at infinity a little bit. Sure enough, you form a supersonic outflow with a shock. That's time going by here. Then you push. You push a little bit, not too hard, and you just push the shock inwards. This is time is going increasing that way. So you have, as you push, you can see these sound waves coming back in and out. They reflect against the shock slowly moves in. Push harder, catastrophe. You go to supersonic accretion with a shock. Now you go back to your original configuration, the one with the shocked wind, but this time remain sitting in an accretion breeze, even though the pressure ratio was the same as before. So that proves that the theory actually works. Okay. So that's the Parker story for you. All right. So that's why the solar wind is supersonic. It can't not be. It's either that or there's going to be inflow. Essentially, it's the only stable solution is that one. Okay. In other words, another way of saying it, if it rains, it pours. A star cannot be in equilibrium with its interstellar medium. It either outflows or it inflows. If you think of it, it's kind of natural. The interstellar medium knows nothing about what's going on at the star. These two things really don't talk that much to each other. When they do, it's very It's going to require very detailed balance of stuff or actually get a breeze going through them, right? Okay, now let's do waves. So we do the linearization again, exactly what I've done before. And what do these equations look like? Well, we start with an equilibrium, so everything doesn't change in time. We have an equilibrium. We'll discuss different types of equilibrium later. And then you have to take the linearized equations. And when you do this, it looks horrible, but it's a linear set of equations. We consider homogeneous mediums to start, so all the equilibrium fields B0 don't depend on it. There's no zero order flow because we're not discussing the solar wind right now. And we can just linearize these equations. And what we do is introduce the Lagrangian displacement. R1 is R0 plus psi. So the perturbed velocity, since there's no average flow, this doesn't work when you're studying Kelvin-Helmholtz, okay? Got to be very careful when you study Kelvin-Helmholtz because the Lagrangian displacement does not coincide with the Eulerian displacement for Kelvin-Helmholtz. But here it does. And then you can integrate in time and write everything in terms of the displacement. And you can write this beautiful equation that discusses, that kind of talks about oscillations. In fact, here I did not even consider that the equilibria are homogeneous. So this equation is a master equation which holds, including gravity, both for stability and waves. But when we do waves, we usually assume the equilibrium to be uniform. When we do that, we take e to the minus I omega t plus I kr. We write a beautiful dispersion relation. And if you look at it, y is the vector displacement. And you'll notice that so you put in now let's put in a mean magnetic field along the horizontal axis. Take a wave vector, which is inclined with respect to that axis, and then take the third axis as being k vector b. So it's perpendicular to the plane containing k and b, right? So that plane, the horizontal plane of the blackboard, is the KB plane, and Z comes out towards you. If you look at that, you can immediately see from here that if I take a perturbation which is perpendicular to both K and B, then this is 0, this is 0, this is 0 because Y parallel, which is Y parallel to B, is 0. You're left with omega squared Y is equal to K parallel CA squared Y. In other words, if I take perturbations out of the plane, I get a wave which has omega squared is equal to K dot VA squared. And if you go and solve for the fluctuation U, you find that UZ in that direction can be either minus or plus BZ over square root of 4 pi rho, depending on the sense of propagation, which is determined by VA, which is the Alfvén speed, which is B over square root of 4 pi rho 0. Okay, so that's the shear Alfvén wave. That's the wave that Alfvén discovered. This wave, which is incompressible because it's perpendicular to K, it's transverse, and it propagates along the field. It's like plucking the cord of a violin. It propagates along the field. The displacement is orthogonal to the direction of propagation. And it has an anisotropic dispersion relation. If you calculate the group velocity, d omega by dk, it's always VA. No matter what K orientation is, the group velocity is always along the field, right? That's really important because it means that the wave does not suffer reflection in geometrical optics. You can't make omega squared negative because omega is K parallel VA. It can become 0 and the group velocity doesn't care. It's always VA. So geometrical optic reflection is when you send light and the speed of light changes and you have omega squared is equal to KZ squared, the vertical part plus the K horizontal part, but C squared changes vertically. So since your horizontal part doesn't change, but KZ has to change because VA changes, and therefore you can get total reflection, right? That's how total reflection works for water and light. So it turns out that the Alfvén wave doesn't do that. Then you get in the plane, you get separate things, and the solution to that equation is written down here. You have a plus sign and a minus sign. You see if I take the plus sign here, this is almost like CS squared plus VA squared. So there's an isotropic, almost isotropic wave which propagates at the sum of the squares of the Alfvén speed and the sound speed, and that's the fast wave. It's a little bit anisotropic. Why? Because the magnetic pressure, remember in the equations of motion, there's magnetic pressure that adds to kinetic pressure, but there's also tension, right? So it's not perfect because if you're parallel to the field, the tension kills the pressure. You go along the field. And so it's almost isotropic, but not quite. The slow mode, on the other hand, the pressure of the magnetic field, B squared, is anti-phase with the pressure kinetic. And so it actually ends up going slower, poor thing, because the two pressures subtract from each other. This is what the phase velocities look like. So here is for beta less than 1, so that sound speed is less than VA. This circle is the alpha waves. Omega equals the K, magnetic field direction is the horizontal axis. This is the K direction. And so the alpha wave is these two circles. Omega equals K cos theta VA. Those are two circles. The fast mode is almost isotropic. You see, it's going around. It's almost like a regular sound wave. And then you have the slow wave, which is this kind of eggy thing inside. I call this kind of Spider-Man. Kind of reminds you of Spider-Man mask, right? Well, it's not clear. More like a Cartman Spider-Man, if you guys know South Park. Anyway, if you look at the groove velocity, something interesting happens. Well, the alpha speed just is sitting at +1. That's the alpha speed. And -1. The fast wave, wow, it's pretty isotropic, right? It goes from perpendicular direction. The sound speed sums up. It's 0.8, so it's 0.64. So you get 1.6 or something. Along the field, it's the alpha speed 1. Slow mode has this weird behavior. It tries to propagate away from the field, but it can't. So it goes out, reaches a maximum angle, and then comes back in. So the slow wave in perpendicular propagation actually propagates along the field, but it doesn't propagate at the sound speed. It propagates at this weird speed called the cusp speed. And you probably know about it because if you have a discontinuity in a plasma, the surface wave propagates at the cusp speed, right? Okay. This is what happens if you change beta. You change beta. So this is low beta. It's kind of a happy-ish Spider-Man. Becomes more and more weird, and it becomes when the sound speed becomes much higher. You notice the sound speed becomes higher. You see that kind of get the impression that the slow mode and the alpha mode are kind of approaching each other, while the fast mode is running away. That's what happens when you become incompressible. When you become incompressible, the fast mode tends to infinity. That's what incompressible means. It means that sound waves propagate infinitely fast. In a solid, the sound speed is much higher than in air. And therefore, that goes to infinity, and you're left with the slow mode and the alpha mode that are the same. And you have two alpha waves in an incompressible medium in the plane. One in the plane and one out. You have two alpha waves in incompressible MHD. You just have alpha waves. You don't have anything else. All right? Okay. See, that cusp becomes smaller and smaller until it becomes a point as CS tends to infinity. All right. But those aren't the only alpha waves we were talking about, right? We were also talking about the humongous wave. So let's look at the humongous wave. The humongous wave is an altogether different animal. You take the nonlinear equations. We don't linearize anything. So we have rho du by dt plus u grad u is minus grad p plus the curl. We can write that in terms of two pieces. The gradient of p plus b squared over 2 mu 0. My students, unfortunately, use MKS. So that's 8 pi in when I see mu 0, I see 4 pi. That's what happens to me. But that's 1 over 4 pi. Now, as I told you, in that humongous wave, this stuff is constant. There's very little density fluctuations. So this guy vanishes. So now we have that momentum equation, which says rho du by dt plus u grad u is equal to 1 over 4 pi b grad b. And then we have the induction equation, which says, well, div b 0, div u 0, b grad u minus u grad b. And here we have minus u grad u plus b grad b. It can be reduced to this form. You can immediately see, once you've reduced it to this way by normalizing everything so that everything is in velocity units, this equation has two possibilities. The second order equation has two solutions. One, little u equal to plus little b, and one, little u equal to minus little b. That's it. You're done. And what happens? Well, we have an average. If you have an average B0, then your fluctuation B1, either this or this as you move on the sphere. And your corresponding U1, if you're propagating along B0, is going to be either this or this, depending on what you choose B0 to be. But you see that your choice in this equation of what B0 is completely arbitrary. You can pull out any B0 you like from this equation. And if you do that, you're finding that the phase speed is going to change depending on what you took for your B0. You're going to have an additional U0. It's arbitrary. But the important point is that if you take the right B0, which is the one where at order 0 there's no perturbation, then the minute you start mucking around with B1, waves that propagate upwards have a positive U1. This is a very strange animal, and we still really don't fully understand how to calculate the separation in terms between the average and the fluctuation, right? Because of this arbitrariness of how to do that. And these are the switchbacks. These switchback patches, total magnetic field pressure is basically constant, as you can see. I won't belabor the point. So how do these things arise? Well, we believe there's an easy way to create these. There are basically two possibilities to generate these things without considering exotic. For me, magnetic reconnection right now is exotic. In a few slides, it won't be exotic anymore. Since we haven't talked about it, let's call it exotic. So let's look for non-exotic explanations. A non-exotic explanation is to say, well, Mr. Velli, you've been looking at this idealized world in which everything is homogeneous. Hey, the sun, you look at density variations all over the place. That means that the alpha speed changes as you move from one place to another. But we know there are swirls in the photosphere rotating these fields around because it's a turbulent thing. And the classic dissipative feature of a hydrodynamic turbulence is to form little swirls. They form in your pool. If you've ever thrown something in your pool and you looked at the shade at the bottom with the eye of a physicist, you should have noticed that there are vortices hanging around for a long time after whatever object you threw is in there. These are solitons, these little vortical structures. Anyway, they happen in the photosphere too. And in fact, they happen so much now that there are papers and almost books written on the swirls in the photosphere. When I started looking at this, there were very few, only the big fat ones were visible. So it was all hypothetical, but now it's pretty clear. So suppose you do this big swirl, that's a torsional alpha wave, it starts propagating out. But suppose that the speed here is a little bit different than the speed here because the density is a little different. Well, then this wavefront that starts out okay starts inclining. And when you do that for a large amplitude animal, you twist it out and you can create reversals very quickly. So that's a very natural way to produce these reversals. Another way, I'm not going to go into the details, I don't have time, sorry. Another way has to do with the gradients. So let's study fast modes because there's this well-known thing, but people don't understand it very much. So I just told you about slow, fast, and alphen. Alphen is K-parallel. The shear alphen is K-parallel. It can't reflect with geometrical optics. The fast mode, on the other hand, well, the alphen speed at the base of the corona is quite low, but it goes way up as you move up. So if a poor fast wave has a little k, which is a little bit inclined, it's going to try coming up, but the alpha speed is going up so fast, just like light trying to come out of water, it's going to be totally reflected. Unless it's coming straight up, then it'll come out. But a fast wave that's coming straight up is an alpha wave. So now we're beginning to see how it's plausible that you could get these large amplitude alpha waves out because anything that's trying to go off to the sides ain't going to come out. Okay? What about the slow? Well, the slow is going to shock. It's a poor thing. It's a density fluctuation. It's going to shock pretty low down. It's going to push the chromosphere up. It's going to make these transients going all over the place. But so that's, I think, what happened. So this is a desperate attempt at showing why you have total reflection. So if you consider the stratification to be only vertical, kh squared is constant, omega squared over va squared minus k squared is ky squared. If va goes way up and kh is significant, this number can become negative, and so you get an imaginary vertical wave number, and so you totally reflect back down. For the alpha wave, on the other hand, there is no geometrical optics reflection. If you have a static atmosphere, you have the conservation of the net upward flux. You write it in terms of the eigenmodes of the alpha wave, which is the upward and downward. These are called Elsasser variables. And you can generalize it. You can write a beautiful equation that you can solve in all its, this is a beautiful equation. It's essentially a relative of the Schrödinger equation. And you can basically solve this semi-analytically and find how much waves are reflected without doing too many calculations. Because you can kind of see, you can see the symmetry, right? You can see that there's a diagonal piece right here, and then there's a non-diagonal piece which has the same sign on two sides. So if you write this in terms of Dirac matrices, this turns out. And basically you can write time-ordered exponential solutions for this. The quantum mechanics people have solved this problem in the 30s, okay? If you put speed in, it becomes harder. Speed changes the amplitude. But you can write an integral for that. It's a relative of the equation that I wrote for the fluctuations in the breeze. You have wave action conservation. And this tells you that the amplitude of the outward propagating wave has a pretty clear dependence on the velocity profile on the alpha and speed profile. So z minus squared is a constant times uva over u plus va. Now this is a very simple expression. It's like xy divided by x plus y squared. That function has a maximum when x is equal to y. So that's a trivial thing. So that means that the amplitude of the fluctuations in the solar wind should maximize around the alpha point where u is equal to va. And it's kind of what we see. Kind of what we see. This is the Mach number, and this is the amplitude of the fluctuations as measured by Parker Solar Probe. And we see that there's a peak in the neighborhood of Mach number equal to 1. It's not bad. It's pretty good. Okay, so I've gone really quick. I hope you guys aren't completely saturated yet. If there are questions on any of these two things, please ask now, because this is going to be the last piece, and it's going to be tough. So.
Question about the outflow and the inflow.
Yes. Inflow. Yeah, it's spherically symmetric.
Yeah.
So you're going to tell me that angular momentum is going to break that symmetry.
No.
Oh, okay. But you're right, if that was the comment.
My question is this.
I think Mera-Wolfer claims that it has happened in the past. There's a whole SHIELD group that has studied the past of the solar wind and the heliosphere, and I think there are some claims that there were periods when the solar wind was shut off entirely and the Earth was directly in contact with the interstellar medium. Inside 1 AU.
Where the flow will stop, it will stop at the center.
Oh no, the shock could be anywhere, depending on the pressure difference, the shock could be anywhere. This is a very simplistic model. There's no magnetic fields, there's no rotation. If you include rotation, it breaks the symmetry. So what happens is the inflow is going to be along the poles, and then rotation, the rotational potential will stop the inflow. You're going to get like an accretion disk or an accretion ring forming at some distance from the sun because of rotation, angular momentum. Yeah. But it's not in the textbook. This stuff isn't, I don't think you've seen it in the textbooks for sure, because it somehow, it's one of those things, you know, maybe in the future. Okay, so let's go back to magnetic reconnection. Really a fun topic, actually. So when I started out doing research, Bruno Coppi was my advisor and gave me an impossible problem to do that involved magnetic reconnection. It scared me so much that I ran away. I went to St. Andrews to work on solar physics. He was looking for fusion plasma. Okay, so how does it all start? Let's look at the Ohm's law. E equals minus 1 over C U cross B plus J over sigma. Where does that come from, actually? How did I get that? Well, sigma, which is 1 over eta, where eta is the resistivity, comes from collisions between electrons and ions, right? So if you really think of it hard, you realize that that E equals minus 1 over C U cross B, if you consider the flow of the electrons and the protons to be the same, is really saying that the force on the electrons vanishes. So what you're really saying is that's the electron equation of motion in which you've neglected the electron pressure gradient and the electron mass because it's so small. Then that would turn into E plus VE over C cross B equal to 0. And if you forget that VE might be difference because there's a current, but V is, if the current at order 0 is 0, then E plus U over C cross B is 0. So let's go back and properly look at the electron equation of motion and write it out fully. Then you get the colored version in the bottom with different colors to explain the various terms in Ohm's law. So what happens is, if you consider that V is different from U is essentially the proton because the mass of the proton is so much bigger that the bulk velocity is U, is VP. Well, you can write VE as U minus VE, but U minus V is proportional to the current. So you can write it as E plus 1 over C U cross B, but then you get this other piece, 1 over NEC J cross B. That's the force on the electrons, okay? Then you have the collisions, Ji over sigma. That's just nu EI VI minus VE. It's the collision frequency between electrons and protons. Then you have the inertia, ME dVE by dt, which I've written in terms of the current. The time derivative plus the convective term. And then there's the pressure gradient of the electrons. And I've changed the color of all of these because I want to discuss their order of magnitude, right? I want to know how big these things are. Which terms are the ones that become important first in my induction equation? So we're going to say that the purple term is order 1. And we're going to divide all the terms by the purple one and find out what their size is. So let's do that. When you do that, this is 1 to 1. And Ji over sigma, if you do the dimensional analysis, you say omega is 1 over tau, sound speed is p over rho. You end up with this thing, that this term here, the ratio of this term is of order of magnitude when it's compared to this is omega over omega p, nu EI over omega p, c over u, where c is the speed of light, squared. The Ohm's this term, which is actually the Hall term, which comes from the current difference between u and VE, turns out to be omega over omega p, omega CE over omega p, c over u squared, where that's the electron cyclotron and that's the electron plasma frequency. This is horrible. It's not a nice expression. We'll make it better in the next slide. Then we get the electron inertia. That's pretty obvious. It's omega over omega p, where that's the plasma frequency squared, c over u squared. And then there's the electron pressure gradient. And that turns out to be sound speed over u squared, omega divided by the proton cyclotron frequency. All right, if you were to guess which one of these becomes important first as omega goes up, which one do you think you would hit first by looking at this? It's hard to tell. Let's go to the next slide first. So turns out that the Ohm's law can actually be better written as omega over omega Ci much less than u over VA squared. So if you ask these things and when you can neglect them, essentially this term here, you can neglect it as long as u over c is much smaller than omega over omega pe squared, right? So it turns into this, omega over omega p much less than u over c. The Hall term turns into omega over omega Ci much less than u over VA squared. And the electron pressure gradient turns into omega over Cp much less than u over Cs, that's Cs unfortunately, squared, okay? So what happens is that in reality, these are for these other terms, the electron pressure gradient is the one that's going to hit the wall first, because the proton cyclotron frequency is much smaller than the electron cyclotron frequency. U over the sound speed can be of order 1. We have sonic flows. So this thing, the proton electron term, is probably going to be the first term to break the Ohm's law, together with the Hall term. Then come collisions. But for simplicity, we use collisions because we like Laplacians and we're used to solving the Navier-Stokes equation. So we tend to do that. You all know that if there is no term like that, and E plus U over C cross B equals to 0, there's a theorem called the Alfvén theorem. You may be familiar and you may be not, that poor Hans Alfvén forswore his theorem. Can you say it that way? He basically reneged on his theorem in his later years. He said, oh, I never should have done that because it's wrong. It doesn't work. And he's probably almost right. Anyway, the theorem states that if you move with a plasma, any closed circuit moving with the plasma, the magnetic flux through it is conserved. So that kind of gives physical reality to magnetic field lines, right? Because if you can't destroy magnetic flux, it's almost as though the magnetic field line existed. That's the proof, by the way. It just comes from dB by dt equals curl of u cross b. If you calculate the flux variation as time evolves, what happens is that if you start here and you ask yourself at a later time, you get this other circuit, how much flux has gone? Well, some of it depends on the time dependence of B, and some of it depends on how much has gone out through that surface. And the two actually compensate each other because of the equation dB by dt equals curl of u cross b. So that's what happens. Another fundamental thing is that in the absence of resistivity, magnetic helicity is conserved. As long as the surface encloses is parallel to magnetic field lines. Okay? That means that you don't have a magnetic field crossing the surface. So in a closed volume made up of a flux surface, magnetic helicity is exactly conserved, A dot B. So along any closed field line, magnetic helicity is conserved. There's another beautiful theorem, it was proven by Vulture, which says that the minimum energy state for a given amount of helicity in the plasma is a force-free field. We haven't discussed what a force-free field is. It's when the magnetic force is zero, J cross B is equal to zero, which means that curl of B is proportional to B, that is called a force-free field. And if curl of B, the coefficient between curl of B, so curl of B has to be parallel to B, so its curl of B is equal to alpha B, where alpha is some function. If that function is a constant, then it's a constant force-free field. Okay, so most of the fields that you've seen are typically constant alpha force-free fields. Okay, what else? If we introduce dissipation, you can write a strict inequality between how much helicity you can dissipate with respect to how much energy. And it's really just a Schwarz inequality. If you write the equation for dH by dt because of resistivity, for example, you get the term up there on the right, J dot B. If you write the energy dissipation, you get J squared. But because J dot B and J squared are related by a Schwarz inequality, i.e. J dot B integral has to be less than the integral of J squared times the integral of B squared, you can say that dH by dt is less than some constant times the square root of the resistivity times the square root of Em times dm by dt. That means that as eta tends to 0, dH by dt goes to 0. But you might say, but if eta goes to 0, so does dem by dt go to 0. No, because nothing stops J from tending to infinity, such a way that eta J squared has a constant value. That's precisely the problem of reconnection. That in the limit, and that's the problem of turbulence. What is turbulence? One definition of turbulence is a system that exhibits finite dissipation in the limit of vanishing viscosity. That's what the role of turbulence is. Turbulence carries energy to whatever small enough scale so that no matter how small the viscosity, you get finite dissipation. In other words, it's telling you something really important, that the limit for eta, comma, nu, where nu is a viscosity, tending to 0 of Navier-Stokes or MHD is not ideal MHD, right? Which is the reason Alphen forswore his theorem. Because if that's true, then it's not true that in general, magnetic flux is conserved, even in the limit of vanishingly small resistivity. All right, so Vulture's theorem, so resistivity breaks the Alphen theorem, leading to possible energy dissipation and relaxation. So the energy minimum principle tells you to go to force-free field, and that's what, and then Taylor generalized this and said, well, wait a minute, locally you dissipate energy, but you end up going to force-free. The total helicity can't dissipate if eta is small enough, and so the total helicity is going to be conserved, but the minimum energy state at a total constant helicity is a force-free field with constant alpha. And that's the Taylor hypothesis. And it's what's behind the production of, say, for example, the reverse field pinch, and most models of flux ropes in the solar wind that you guys are ever going to see, because they're typically force-free states with alpha equals to constant. So that's the basics. But we're back to the problem of the solar flare and coronal heating. So the flare is rapid energy release. Coronal heat is integrated rapidly energy release. Remember, one large flare corresponds to about 100 hours of heating on an active region, all right? So you end up releasing 10 to the 32 ergs, length scale 10,000, a bit more kilometers. In time scales, less than 20 minutes or so, okay? So how's that possible? Well, a long time ago, people faced with the Alphen theorem started thinking about how resistive effects might work. And so Thomas Gold, I think he was the first one, suggested that reconnection should happen. So you should locally dissipate magnetic energy in magnetic reconnection. Soon after that, Dungy invented the Dungy cycle. We saw it yesterday in the lecture, where a magnetic field of opposite sign relaxes, brings the field back, etc. At the same time, Sweet tried to calculate the rate of reconnection. So Sweet calculated a stationary state reconnection picture, goes to a conference. Gene Parker's sitting in the audience, just like you guys are sitting in the audience with me. Sweet gives his talk. Gene says that's all bullshit. Does his own calculation, finds that Sweet's actually right, but it's so slow that it's useless. Parker goes home, sends the paper to the journal before Sweet does. So he scoops Sweet, but he does mention Sweet in the paper. That's why it's called Sweet Parker. You may have not read the original papers, but you should. Parker's name is associated because it's a negative result, not a positive result. He says that's the conclusion of his paper. The observational and theoretical difficulties with the hypothesis of magnetic field annihilation suggest that other alternatives for the flare must be explored. He's claiming that Sweet Parker is too slow, and he's right. Why? Because you have opposite magnetic fields. You have a sheet of length big L, thickness little l, and you're going to burn this field by bringing it in with a flow, and you have to conserve mass flux. Flow coming in, flow comes out. But how fast can the flow come out? The maximum speed you're allowed is the Alfvén speed. But that means that the inflow speed, or the outflow speed, when you include the fact that you have to have mass conservation, flux conservation, L over L scales like S to the minus 1/2, where S, big L VA over E to M, where eta M is the magnetic diffusivity, is the Lundquist number. Turns out that when you do this calculation, the typical timescale energy release is between 3 and 30 years, not really of the same order of magnitude as 20 minutes. And so, whoops, that's done. Okay, that's 1958, 1959, 1960, Sweet, and Parker, 1963. At the same time, Cyrilotsky was saying, but wait a minute, there's got to be something wrong with this. When you thin a current sheet, there's going to be time dependence going on. Can't really neglect that. Anyway, he wrote a series of papers, beautiful papers about this. It didn't do many calculations. But in the early 60s, people were trying to make machines in the lab. And the tokamak had a big problem, that the column, where the current was, started oscillating violently and ended up banging against the wall and stopping the discharge. And these were called a sawtooth oscillation. And Kadomtsev had a model, but it appeared that you needed dissipation in this thing. And the most potential thing was that the current sheet was unstable. And so first Killeen and Rosenbluth in 1963, and then my advisor, Bruno Coppi, in 1965, wrote a series of papers on the instabilities of current sheets in various configurations, Coppi, Green, and Johnson. Anyway, the typical situation is a current sheet like this, a simple one-dimensional, infinite current sheet in which the magnetic field changes sign, like so. And it can be like a hyperbolic tangent. That's called the Harris sheet for simplicity. And you can make two varieties. You can make it, you can put a pressure in there to solidify this thing, or you can make it force-free by having it rotate around. Instead of going through a neutral point at the center, B is going in the Z direction. So it just rotates around instead of going through a zero. Well, then you can perturb this thing and write down the equations. And the equations are going to end up being kind of a mixture between slow and Alfvén waves. But now remember, the equilibrium has a gradient in it. So the equation is a little bit more complicated. And you're looking for solutions of the type e to the gamma t. And this is what the differential equation looks like. Now B0, your equilibrium field, depends on a coordinate perpendicular to itself. And so at the time, we didn't have big computers. So people had to find smart ways to solve these equations. And what people recognized with the resistivity here was a small perturbation. In fact, it was a singular perturbation. Exactly like Navier-Stokes or resistive MHD is a singular perturbation to the ideal equations. Why is it singular? Because without that term, the equations are lower order than when they're there. When you do something like that, new solutions appear. when you add this, because there are modifications due to the small parameter of the old solutions, but then you have completely new solutions that didn't exist in the old system. That's why it's important. So where's the singularity? Well, you can kind of read it here. If you put eta to 0, this term vanishes, right? And so now we have the frequency with the imaginary frequency, because we're looking for stability or instability, gamma b, and you have ikb0v. But b0 vanishes at the center of the sheet because it's going through 0. That component vanishes. So this term here goes to 0. In fact, linearly, it goes like x. Okay? So that means that v goes to infinity. If this term on the left is finite, v has to go through infinity. And so what happens is that you have an inflow, and contrary to Sweet Parker, that inflow isn't happy. It's not just going, nyeh, nyeh. It's going, it's accelerating as it comes in. And it's going to have to crash when it gets to the center. And that crash can only happen if you put some resistivity or viscosity in there. And it's going to allow the crash. So these guys, they said, well, okay, so let's do this. Let's find a solution outside where we can forget about the crash. Then in the middle, we can linearize the field. We can say that it's just proportional to x. Solve that inside. Take the limit of that inner solution as x becomes big. Make it continuous with the solution of the outside when x becomes small. We match them together and we find gamma. That was the trick. As a result, the important parameter that comes about is called delta prime. You can see from here that the derivative of b, of little b, of the perturbation, has to be discontinuous in the ideal limit. There's no way it can be continuous because v goes to infinity, so everything crashes. So as you come in from one side, you go like this. Come from the other side, it goes like this. There's a cusp there. There's a discontinuity in the derivative. Turns out that's fundamental to the instability itself, delta prime. There, okay? Anyway, when you solve for various small values of resistivity, this is what you see. So this is what the velocity field does. You see, it really tries to go to infinity, and then it's regularized by resistivity. And this is the magnetic field configuration. And what do you find? Well, you find that the fastest growth rate is proportional to s to the minus 1/2. So it's slow again. But there's a little sleight of hand that's happened that I haven't mentioned. Where's the sleight of hand? Sleight of hand is that this current sheet is infinite, and the only unit of time that I have is its thickness. So when I define my Lundquist number here, I've used the thickness of the sheet. S is AVA over eta m. Keep this in mind. It's really important, okay? So it's slow, but on a time scale set by the thickness of the sheet. So the clock of the instability is slow, but it's set on an Alfvén time, which if the thickness of the sheet becomes small, is, so if you can be long, but if your second lasts nothing, it might be finite. See where I'm getting at? All right, you can study the instability in different parameters as the wave number changes, et cetera, and this is what you find. You find that there's different regimes. At small wave number and relatively small s, there's a faster mode that goes like s to the minus 1/3. When you go to very large s, though, things slow down, and they go like s to the minus 3/5. That's the mode that is called tearing in the Firth, Killeen, and Rosenbluth. The famous tearing mode is s to the minus 3/5. However, if you look at the envelope of all the solutions for different k's, it turns out that the cusp between s to the minus 1/3 and s to the minus 3/5 changes as you change k in such a way that if you throw k out by taking the envelope of all the solutions, they go like s to the minus 1/2. That's the fastest mode. So it turns out that when I was in St. Andrews as a postdoc, Dieter Biskamp, who's a German numerical simulation guy, came over. Eric Priest is famous for having generalized Sweet Parker to various configurations, et cetera. And he was trying to do simulations of Sweet Parker. And he was finally getting up to pretty high resolutions. Instead of 100 by 100, which means your resistivity is 1/100, it's really big. He was getting up to resolutions like 500 times 100, 1,000 times 1,000. These were big in 1986. I'm talking about 1987. These were really big resolutions. Create Sweet Parker current sheets. Saw tearing. He wrote a whole book, blah, blah, blah. And he's trying to figure out, is Sweet Parker stable or unstable? And Shibata-san, very bright Japanese astrophysicist, together with a fusion guy, Tajima, US, played a game. And they said, wait a minute, let's go back and consider this sleight of hand that I just made. S, the Turing mode is AVA over eta. But S in Sweet-Parker is with big L, not little l. Let's renormalize. Let's calculate tearing, but introducing the renormalization. What happens? Well, you do the renormalization. Tau A becomes L over VA. S star is big L VA over eta. And then you translate the S star into S with L. You find that your new gamma tau A star scales like S star to the 1/4. In other words, if the Sweet-Parker current sheet is unstable to tearing, it's unstable with a growth rate, which on the alpha n time calculated along the length of the sheet, goes like the Lundquist number based on the length of the sheet to the power plus 1/4. All right, now get mad at me. Why is that a paradox? What happens when you become ideal? The resistivity goes to 0. But the resistivity is LVA divided by, the Lundquist number is LVA divided by eta. So what happens to S? It goes to infinity. What happens to the growth rate as S tends to infinity? If it's proportional to the 1/4 power, it goes to infinity. That can't happen. And yet, not only were people happy about it, this is an exercise. This calculation is an exercise in a book by Shibata and Tajima. It's called Plasma Astrophysics, chapter 7. You can go look for it. It's a problem. Show that. This was completely forgotten by our community. People weren't thinking about it. A PhD student, Loureiro, discovered it again and wrote a PRL or something like that, and they published it, even though it was already in a book. And then he came to a conference. I was sitting in the audience, and I saw this, and that word flashed in my mind. And so I put my hand, I said, surely Nuno, because he was actually counting the plasmoids and counting how many instabilities there were, how many islands. And I said, you know, clearly that's really telling you something different. It's telling you that you can't form a Sweet-Parker current sheet. Why? Because if S becomes big enough, the time scale over which it breaks apart is faster than whatever time you use to put it together. And as if you ever tried to put a pencil in equilibrium on its point, you just can't do it, right? It's not a question of asking if it's unstable. You just never can produce that equilibrium. It's so fast that you can't do it. And I got an answer which was not very satisfying, let's put it that way. And then Amitabha Bhattacharjee was also there. And he gave a similar talk and he counted the plasmoids and stuff. And I put my hand up and again, but surely that can't be right. And I was told, and I'm saying this with the spirit that you guys should think the same of what I'm saying to you. He told me, you haven't thought about it enough. Okay, I said, so I'll think about it. So I was driving home from Yosemite. This meeting was up in Yosemite. I was going back to Los Angeles, and I thought about it. And then I said, I have to give my student a calculation to do. And we came up with this. So we said, wait a minute. Fast reconnection should exist within resistive MHD. It's given by the proof that the Sweet-Parker current sheet, maintained by a flow field with an appropriate inflow-outflow structure, could be unstable to reconnecting instability, which grows without bound as the Lundquist number tends to infinity. Now, it turns out that if you have S small enough, you can do Sweet-Parker. So the requirement for S in order for plasma to kin does little to resolve the paradoxical nature of the result. Why? Because if S tends to infinity, you're screwed. You can't form it. That's what I say. We argue against the realizability of Sweet-Parker current sheets in aspect with a large S by showing that an ideal tearing mode, i.e. a mode which has a growth rate which is compatible with ideal MHD, kicks in before you ever get there. And while the Sweet-Parker current sheet thickness scales as S to the minus 1/2, the tearing mode becomes effectively ideal when a current sheet collapses to a thickness of order S to the minus 1/3, up to 100 times thicker than S to the minus 1/2 when S is large, blah, blah. Okay, you can imagine the reaction from the reconnection community. So this is the reaction that happened. It's really funny. You're wrong. You got to be wrong. Absolutely wrong. Oh, we all knew. That's the transition. There was like a phase transition. So now it's fully accepted. Well, it turns out that if you ask yourself how it scales with the aspect ratio, you say, okay, let's take an arbitrary sheet with some width A and length L, and let's ask what the growth rate. And you find the growth rate scales like S to the minus 1/2 times L over A to the 3/2. And so you can't do anything that's faster than ideal because MHD works on ideal timescales. So what we're really saying is, look, the limit, the point of the paper was to say the limit of resistivity going to 0 or the non-ideal terms in Ohm's law going to 0 is not ideal MHD. It's ideal MHD where everything is smooth. But in local places where things get tricky, you can have reconnection. So you can break Alfvén's theorem effectively in ideal MHD on timescales that are compatible with the Alfvén time. Anyway, so we then did a nonlinear simulation of the tearing mode, and you probably don't remember the magnetic field profile that I showed you, but it looked something like this black line. And when you let this thing go, what you see is that the current sheet collapses. It starts to tear. You form little X points. Those X points collapse again, and they become thin sheets themselves. And they tear, and they form little X points at smaller scales, and they lengthen, and they tear. And this whole thing is recursive. It goes bang, 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 bang. And very quickly, you go to 0 scale. So you get finite dissipation. And so this is actually proof that that's what works. This is what happens. So these are the 3 profiles of the magnetic field at time 18, 19, and 19.8 Alfvén times. And what I'm doing in the inset is I'm magnifying the central part. So you'll see that at time 19, the central part of the red curve looks like the black curve. When I magnify, the red that does something weird, it's a much smaller scale, actually looks like the black curve. And the blue curve, which looks different here, when I magnify at time 19, looks like the red curve at the previous time. So everything goes together. And then, so then you remember the tearing mode theory that was built by our fathers, which had this singular layer inside. And then you understand. So this is 2-dimensional, but it's simple. So in 2-dimensional, tearing takes place through the singular layer. Singular layer has an inflow and an outflow. That creates the X point. Turns out that the outflow actually stretches the X point. Things are diffusing in that singular layer, so it doesn't thicken because there's an inflow. So it's now an equilibrium between the inflow coming in and the diffusion. So that little thickness delta becomes long. It's a current sheet. So now you have to calculate the Lundquist number on that length and find out when it hits a critical value so that it can become unstable on an ideal timescale. When that happens, it breaks apart again, and so on, and you go to 0. And Shibata and Tanuma had this idea already, but they hadn't realized that you couldn't do it on Sweet-Parker. You had to do it on something a little bit thicker. Anyway, you get this kind of hyper-progressive geometrical progression. So the Lundquist number at step n scales like S to the 3/4 to the n. And so you very quickly go to 0 scale, and you end up in turbulence. And this is what happens to one case of a current sheet that does that. And now there's abundant evidence that this happens. And in fact, the tip of Helmut streamers is a specific place where this thing can go on. And we think that those plasmoids are the result of something like that. So, to conclude, this Kump had kind of figured out that something was going on. And this is the end of his book. He has a book called Magnetic Reconnection. And you can read this. Magnetic and solar corona is a particularly attractive playground. He was talking about trace. Since trace, we've had SOHO and SDO and Muse and Iris. So we're getting better at looking at these very small scales and finding signatures of this local heating going on. And he ends with this citation from a very famous song that you probably have all heard. And I'll stop there. Thanks. No questions. So the reconnection that I'm talking about here is linear. It's the beginning. It doesn't address multiple things. So it doesn't address, for example, well, let me add before you ask questions. So this technique of renormalization can be generalized to whatever breaks the Ohm's law. And if you use it in a smart way, you've heard probably about electron-only reconnection. You've heard of that? Why does that happen? Because I'm telling you everything in terms of an aspect ratio. A over L has to be less than a certain amount. And because the paper that we wrote, we were thinking of about a natural system where the length could be anything. We weren't worried about the length. But suppose you have a system that is blocked. The length is blocked to some size. And when A over L has to get smaller, it doesn't satisfy the criterion at an ion scale. The tearing is too slow on the ion scale. So that means it has to collapse further until the time scale becomes ideal. And that scale happens to be the electron scales in such systems. That explains why sometimes you see electron-only reconnection, but not always. If the system tends to be infinite or large, you don't see electron-only reconnection. So on. And so there's ways to generalize this to electron pressure gradient driven, electron inertia driven reconnection, and so on. But it's only the initial phase. Then you go to turbulence, and that would require a whole different chapter. It's fascinating because when people talk about turbulence, they talk about the nonlinear time. And what happens when you look at a big simulation of turbulence, you'll notice that people consider that the inertial range is formed over one nonlinear time. But if you look at the way current sheets form and reconnection happens, it happens before. Reconnection is faster than your nonlinear turnover time. In fact, it looks like that the Kolmogorov idea of the cascade where things happen top down isn't right. Reconnection intervenes by directly coupling large scales. See, it's very anisotropic, right? Because reconnection doesn't really touch this scale. It touches this scale. So it's very anisotropic, but it's like a telegram that's directly communicating very small scales to very large scales. And so it looks like, in fact, that inertial range, which looks Kolmogorov-like, is actually built top down and bottom up, thanks to tearing happening before you get to one full nonlinear time. But this is, it's being work in progress. There are models out there. You can read papers by Boulder, Nuno Loureiro, but they are still thinking in terms of reconnection cascading things down. But that's not quite right, I don't think. Anyway. Yeah. Oh, in this case, it's resistivity, right? So this is what happens. It has to be resistivity. So it turns out that the singular layer has to take the flow and bend it over and go through zero. Essentially, you have this flow that wants to diverge, and resistivity basically bends it over and makes it go to zero. So if you ask yourself how thick, if you take the ideal, what I call the ideal current sheet, which is thicker than Sweet Parker, and you let it tear, and you ask yourself, how thick is the singular layer under tearing of that current sheet? Guess what its thickness is? Sweet Parker. But it's not stationary. It's an instability. It's growing exponentially. The time scale is going down as time goes up. Yeah. Anyway, so it's a fascinating nonlinear thing that we're getting. I think we're touching, in the simplest case, resistivity and viscosity, the nonlinear aspect of turbulence. And I think we have people that are going to show big simulation. I don't know if you're I'm not sure, but I presume that's what you're going to do. And so I think, progress is happening, and as Biscamp had kind of mentioned. So, but I think we're getting there. And of course, there's many other aspects of it, because when it's not resistivity, you have to partition the energy between heating and particle acceleration, and then you have all sorts of other phenomena going on that have to do with the behavior of particle orbits in this magnetic field, in these islands that are moving around, Fermi mechanisms, and so on, Betatron, all these kind of changing magnetic fields that can do stuff to parts of the distribution function, leading to acceleration and so on. So, all this is kind of open for you guys to research. Where does it fit? Where does it fit? So it turns out that pet check reconnection, which involves slow shocks emanating from something that looks like a Sweet Parker, smaller than a Sweet Parker current sheet, is not easy to produce in homogeneous systems where the resistivity is quasi-uniform. You can get it if you have strong changes in the thermodynamic parameters of the plasma from region to another. So if you have a boundary layer between different regions, then you can form this kind of quasi-stationary Pechek-like configuration. Right. But it requires inhomogeneity in the basic plasma parameters. For example, of the resistivity. The resistivity has to change. If you take a region with with very small and a region higher resistivity, you can form a Pechek-like layer around the region of high resistivity. So what Loureiro and Boulder and Mallet and Ben Chandran have done is that what they've taken this idea of ideal tearing and they've applied it to a turbulent cascade. So because they believe that the turbulence is anisotropic, basically the eddies in their view become very stretched out. They look like current sheets. And at some point, the tearing instability becomes competitive with the nonlinear time and therefore changes the spectral slope. That's in their models. As I said, I think it's incomplete because tearing happens before the nonlinear time. So it's actually even faster than that. And it happens so when you start off an eddy simulation, there's a boundary between eddies. And the stretching of eddies is not uniform in your domain. The difficulty of tearing is that it happens in physical space. Turbulence models typically happen in Fourier space, but they don't talk to each other very easily, right? So what happens is you form localized region within your whole domain where you form current sheets, and the current sheets break apart. And that develops part of that inertial range cascade separately from, so I don't think the picture is complete that way. Yeah. Sure. Sure. Oh, yeah, no, of course. I implied it, but I didn't make it explicit. So the first term that actually breaks the things is the electron pressure. And MMS has shown that in a very clear way. The non-gyrotropy of the electron distribution function and therefore pressure gradient effects are fundamental. That's where the reconnection happens. It's not resistivity. And so the caveat here is that I think similar things are happening, but there is no real model that uses, I mean, the linear part with electron pressure gradient has been done. We've actually done it. And others too. Alfred Mallet has done it as well. But the 3D version of this, where, in 2D, you can get this kind of self-similar behavior. In 3D, these X points are pointing at you and these things can kink around you depending on how much axial field you have. And there's not many simulations the theory becomes very difficult to do, obviously. And so there's a lot to be done there, I think. But the first indications are that it's clear that the driving mechanism is kinetic. It's not resistive, for sure. Yeah, right. Yeah. Oh, it starts with more than one. Yeah, because little k, big L is so in the Sweet-Parker case, when they were counting plasmoids, the fastest growth rate has KL proportional to S to the 3/8, almost square root of S. So if you have S 10 to the 6, you get 1,000 islands, right? In the ideal tearing, it's much smaller than that. KL scales like S to the 1/6. So if you have S equal to 10 to the 6, you get 1 or 2 islands, 3 islands, not more. The question, what's the effect of S in these systems that we're dealing with? So in these simulations here, the S is typically a couple of million or something like that. And initially you don't have many islands in our system, but as it takes forward, you get more and more islands going in. So the other paper you should read is Shibata and Tanuma 2001, which is the ones that kind of realized that there could be this self-similar cascade of islands happening. I should have mentioned another very important fact. Sorry, things pile up, and we're trying to go simpler to more complex. So the Hall term is also very important, and MMS has also shown that. So the Hall term kind of widens the outflow around the X point. It kind of introduces a quadrupole magnetic field whose effect is to stop the X point from collapsing. And so depending on how fast you reach the Hall scale, you can interrupt this system, but you'll still get finite reconnection. The Hall term accelerates reconnection. And you can do the linear theory of that as well. That also exists already. So it's not true that this ends up to zero scale. It depends on the kinetic scales that, you stop being MHD at some point as you're going to smaller and smaller scales. So you have to hit Hall, electron pressure, et cetera, sooner or later before you hit, zero scale.